this video, we are going to look at 10.2, which is electron diffraction. So we are going to describe the observation of electron diffraction in Davison-Germer experiment. And then we are going to explain the wave behavior of electron in an electron microscope. And finally, we are going to look at the advantages of electron microscope compared to optical microscope. So this is the electron diffraction experiment, and this is the setup of the experiment. So we can look at the diagram that shows the electron diffraction tube. So we will have electron which will flow from cathode to anode, and then it will go through the electron diffraction, and what we will see on the screen is a diffraction pattern which look like rings. This experiment actually proves that the de Broglie relation was right, and we can find the wavelength of the electron by using lambda is equal to h over mv, where m is the mass of an electron and v is the velocity of an electron. If the velocity of electrons is increased, we can see that the rings will be narrower, because the wavelength of electron will decrease with increasing velocity, as predicted by de Broglie. So de Broglie tells us that lambda is equal to h over mv, where we can see that lambda is inversely proportional to velocity. So if v increases, lambda will decrease. And that the velocity of electrons are controlled by applied voltage V across the anode and cathode. So U is equal to K, in which U is EV, K is half mv squared. And then we can rearrange this equation to get V is equal to the square root of 2 EV over m. So we have the de Broglie relation, in which lambda is equal to h over mv. And then we know that V is equal to the square root of 2 EV over m. So we can substitute this V into the equation. Then we will get lambda is equal to h over m, the square root of 2 EV over m. And then we can also get this in the form of h is equal to square root of 2 meV. We have to note that electrons are not the only particles which can behave as wave. So the diffraction effects are less noticeable if we have massive particles, because their momenta are much higher and wavelength will be shorter. We know that lambda is equal to h over mv, where mv is momentum. So if momentum increase, lambda will decrease. And then the diffraction of the particles are observed when wavelength is of the same order as the spacing between the plane of the atom. Let's look at example 10.4. For question A, electron is accelerated from rest through a potential difference of 2000 volt. Then we have to find the de Broglie wavelength. And then for question B, electron and photon has the same wavelength of 0.21 nanometer. So we have to find the momentum and energy in electron volt for both electron and photon. Since we are given the potential difference, we can find the de Broglie wavelength for electron by using the equation lambda is equal to the h over the square root of 2 meV. And then we just have to substitute in the values that are given to us. So h is the Planck's constant, 6.63 times 10 to the power of negative 34, and then divided by 2 the mass of electron, and then E, and finally the potential difference, which is 2000. And then we will get the wavelength 2.75 times 10 to the power of negative 11 meter. Question B wants us to find the momentum and energy for electron and photon. So for an electron, the momentum, to find the momentum, we know that the wavelength of the electron is actually the same as the wavelength of the photon, which is 0.21 nanometer. And then we want to find P. So P can be found by using the de Broglie relation. Lambda is equal to h over P. And then we just have to substitute the values of Planck's constant divided by the wavelength of the electron to get P is equal to 3.16 times 10 to the power of negative 24 kg meter per second. And then for the energy, We can find the energy of electron by using the formula for kinetic energy, in which K is half mv squared, and we know that momentum is equal to mv, so we can get v is equal to p over m, which we will substitute in this equation, and then we will get K is equal to p squared over 2me, and then substitute in the values of p and also the mass of the electron times by 2, which will give us 5.48 times 10 to the power of negative 18, but this is in joule, so we want our answer to be in electron volt, so we have to divide this with 1.6 times 10 to the power of negative 19, and our answer will be 34.3 electron volt. Now we want to find the momentum and energy for a photon. So for a photon, first we know that the wavelength of the photon is 0.21 nanometer, and then to find the momentum we have to use the de Broglie relation, so we will get P is equal to H over lambda P, which will give us the same answer as the momentum of electron, 3.16 times 10 to the power of negative 24 kg meter per second. And then to find the energy of a photon, we have to use E is equal to hc over lambda P, and H is the Planck's constant, times by the speed of light, 3 times 10 to the power of 8, divided by the wavelength of the photon. And finally, we will get energy 9.47 times 10 to the power of negative 16, divided by 1.6 times 10 to the power of negative 19 to get our answer in electron volt. Example 10.5 wants us to compare the de Broglie wavelength of electron and proton if they have the same kinetic energy. So we want to compare the de Broglie wavelength in terms of kinetic energy, which is why we are going to use this formula. And then we know that EV is actually equal to the kinetic energy. So that's why we are going to replace K into this equation to get lambda is equal to H over the square root of 2mk. The question mentions that electron and proton have the same kinetic energy, so Ke is equal to Kp, which is equal to K. And then the question asks us to compare the de Broglie wavelength for electron and proton. So what we have to do is find the ratio, the wavelength of electron over the wavelength of proton. So wavelength of electron will be H over square root of 2mek, and wavelength of proton will be H over square root of 2mpk. And then what we can find from here is that the H will be cancelled, and then the square root of 2k will also be cancelled. And what we are left with is the square root of mp over me. And then we have to just substitute the values of mp and me to get the ratio, which is 42.8. Okay, now we are going to look further into electron microscope. So these are the images that can be observed using electron microscope. So the electron microscope is actually a practical device which relies on the wave properties of electrons. It is similar to optical compound microscope, but it has an advantage in which it has a resolving power which is much higher than the optical microscope. And this is because the electrons can be accelerated to very high kinetic energy, which will give them a very short wavelength, typically 100 times shorter than those of visible light. So we can see the diffraction effect of electrons to be much less than that of light. And as a result, electron microscope can distinguish details about 100 times smaller. Okay, now we are going to look at the operation of electron microscope. So in operation, a beam of electrons will fall on a thin slice of sample. So the sample or specimen must be very thin, only a few micrometers, in order to minimize the effects such as absorption or scattering of electrons. And then the electron beam is controlled by electrostatic or magnetic lenses in order to focus the beam to an image, and the image is going to be formed on a fluorescent screen. So there are actually two types of electron microscope. First one is transmission type, which produces two-dimensional image. And the second type is scanning type, which produces images with three-dimensional quality. Okay, we have this figure here which shows the diagram of light microscope, and then transmission electron microscope, and finally the scanning electron microscope. Let's look at the images observed under each microscope. For light microscopy, we will get image which is viewed directly like this. For transmission electron microscopy, we will get this image which is viewed on a fluorescent screen, and it is two-dimensional. And then finally for scanning electron microscopy, we will get image viewed on the monitor, and it is three-dimensional.